This brief lecture will cover the topic of transforming scores, or more specifically, entire distributions of scores. And there's a number of reasons why we might want to do this. Consider the following example. Say that you're lucky, you're going to Barcelona, Barcelona, Spain, and you look up the weather report to see what the weather's going to be like so you know how to pack and plan ahead, and you get a weather report such as the following. Like the rest of Europe, Barcelona uses the metric system and reports temperature in regards to temperature in Celsius. And so you see here, current temperature is 17 degrees. The planned temperature for your upcoming trip, 18 degrees Celsius. And you might be saying, well, wait a minute, exactly what does this mean? Is this warm? Is this cold? How exactly should I pack? And so what you may need to do is to convert that temperature into Fahrenheit, a temperature that you might more readily understand. Well, when you're doing an operation like that, that's exactly the type of transformation that we're talking about. You have one sort of measurement scale, in this case temperature in Celsius. And what you want to do is to transform that and convert the scores into some other measurement scale, in this case Fahrenheit. It's really that simple. Now in terms of research, there's a number of instances why we might want to do this. Let's say that we've collected data on this 8-point scale like we did with your class survey at the beginning of the semester. Well, if in another class they've collected the same data, but due to lack of coordination or whatever the case may be, let's say that they recorded the exact same items, but they recorded them on a 5-point scale or a 10-point scale. Well, now what we may want to do is to compare the data we got from our class to the data from this other class. But because they're measured on differing scales, we can't directly compare them. A 4 on our scale is the midpoint, whereas on a 5-point scale, a 4 is a very high value. So what we need to be able to do is, again, convert both of those surveys to the same sort of metric, the same standard scale, which we actually do call standardization. And by that process, then, we can directly compare scores coming from two different samples or populations, from two different administrations of a survey or any other instrument where these things might not be naturally aligned. So that's the situation that we're going to be looking at today. Now again, as I mentioned, there are many reasons we might want to do these transformations. Some very basic ones in terms of just converting measurements. We also might want to look at things in terms of deviation scores. What I mean by that is we might want to know how far above or below average somebody is rather than their individual raw score. So we might take scores on an exam, for example, and convert those raw scores to something like deviation scores. Or we might want to change the scale endpoints, which is the example that I mentioned previously. Think about one last example. Let's return to that class survey example for 1 minute. And let's think about two different people who responded to these items. Now we're going to learn a little bit more about survey response biases later when you're creating your own surveys. But think about one person who's responded by checking off these values here. Lots of 7s and 8s. They're strongly agreeing with pretty much every statement that we're seeing here. Now there's nothing inherently wrong with that, but think about somebody else who's responded with the following responses on the scale. 4, 2, 7, 8. They're all over the board. They agree with some items, disagree with others. Well, now in this case, even across two different people, a value of, let's say, 6. So if we look at item number 7, both of the hypothetical respondents here have provided a numeric response of 6 on this item. But what does that really mean? For the person whose checks are in red, that's the lowest response they've given. So for that individual, that's relatively a weak agreement with that item. Because they're so strongly agreeing with everything, they're sort of pegged at the top end of the scale regardless. A 6 actually means, again, relatively for this individual, a low degree of agreement. Whereas for the blue individual, they're using the entire scale, and a 6 for this individual represents a substantial degree of agreement. And so even the same number across different respondents or individuals can sometimes carry different meaning. So in this situation, what we may want to do, another situation where you might see something like this, is when individuals are rating something, attractiveness, or even judges' scores in the Olympics. Situations where you might have a lot of disparity or idiosyncratic use of the scale by different individuals responding to your survey, or whatever it is to which they're responding. What you then may want to do is to similarly standardize or equate these scores across individuals as well. So that's one more example. All of these are going to be based on the same underlying logic. That is, we're going to be applying certain mathematical operations to an entire set of scores in order to change one set of scores to be in line with another set of scores, or to just change one set of scores to carry a different meaning, such as Celsius to Fahrenheit temperatures. Now, in order to compare these scores, again, it's helpful to transform them, as we mentioned, so that they are standardized. The definition, then, of scores that have been standardized are those that have been transformed such that they are on the same underlying scale. Now, what we mean by transforming these variables is nothing magical. All it involves is adding, subtracting, multiplying, or dividing a certain number to each and every score on some specific instrument or some specific scale. That's it. Now, these types of transformations are what are referred to more specifically as linear transformations, when you're just doing these four basic operations: adding, subtracting, multiplying, or dividing. There's a lot of other things we can do, but we're not going to be talking about those right now. Now, again, when variables are represented by the same underlying distribution, that is, if we have two distributions of scores that have been transformed independently, right? So I might add, subtract, multiply, or divide numbers to one set of scores and do the same types of operations with different values on a different set of scores, so that those two variables have the same underlying distribution, that is, the same mean and standard deviation. In this situation, then, we refer to those two different sets of scores as being standardized. Now let's look at some examples to see exactly what we're talking about here. As I mentioned, when we transform these scores, we're going to perform four basic operations. In reality, those of you that are very good at mathematics realize these are actually only two different operations. Addition and subtraction being essentially the same thing. It just matters whether or not you're adding or whether you're adding a positive or a negative number. And multiplication or division, which is again the same thing as multiplication, just with a reciprocal. Now, the important thing to understand here, okay, this is the key point, is that when you're adding or subtracting values to a set of scores, what that does is that will shift the entire distribution over. Now, what this means is that it will affect the mean of that distribution, but not the variance. So we talked about the mean as representing the location of the distribution. Well, when you're adding or subtracting score values to these scores, what you're doing is you're essentially sliding or moving the distribution up or down. You're changing its location, but you're not changing its variance, that is, its spread or dispersion. You're not stretching the distribution out or shrinking it any. However, that is what you're doing when you do multiplication or division. And for that reason, multiplication and division operators will affect both the mean and the variance of a distribution. It's equally important to point out here that the distribution shape cannot be affected by these four basic operations. That is, if you have a normal distribution, you can't add, subtract, multiply, or divide anything to it to change its shape from a normal distribution. And similarly, even if we have, say, a skewed distribution, there's nothing we can do with these four basic operations to make that distribution more normal. It is still going to exhibit the positive skew that the original distribution exhibited. It's just going to have a different mean and standard deviation or variance, potentially based on the operations that we're doing. So again, let's think of some examples here. Take this distribution here, right? And we've used this to illustrate a couple concepts in the past. So what we have is this basic distribution here with a set of scores. And let's say that we calculate the mean on this set of scores, which we find to be 13.55, represented here by the orange arrow. So 13.55 is the mean of this distribution. What if we apply some of the transformations that we talked about? We also have, a standard deviation of this sample of scores of 4.70. So now let's apply some of these transformations that we talked about. Let's start by transforming each score, x, by subtracting 13.55. This would be an example where what we want to do is to transform this set of scores into deviation scores. Because what we're going to be doing when we do this, right, subtracting 13.55, that mean value, from each and every score, what we're doing is we're shifting the entire distribution to the left by 13.55. So each and every score has had 13.55 subtracted from it. Okay? So for example, that score that was up there at 30 has had 13.55 taken away, and now it's showing up at 16.45. Importantly, that mean of 13.55 has had 13.55 taken away, and therefore it is, of course, showing up as a value of 0. That is now what we've done, is to change this set of raw scores into a set of deviation scores, because now any value that's positive, i.e. greater than the new mean of 0, will be above average, And any score that is negative, less than the new mean of 0, will be below average. So we can very quickly tell by just the sign of somebody's score, once we've converted into deviation scores, whether or not they are at least above or below average. And then the number would then tell us how far above or below average they are. Now I'm going to slide it back over here so that it's a little bit easier to see here on the screen. Okay? But in this sense now, again, what we've done, notice, as we mentioned before, by adding or subtracting, in this case subtracting a value, what we've done is to shift or slide the entire distribution down, as you saw. And notice that that's affected the mean. Okay? Because we know those operations, addition and subtraction, do affect the mean. But we know those do not affect the variance. And as you can see here, these scores have not spread out or gotten any closer together. So none of the points are any further on average from the mean. Recall that's our intuitive definition for variability. So none of these points got closer or further to that mean, but the mean, as well as all the points, did in fact change. That's all that's happened here, rather than any stretching or shrinking, any spreading out or bunching up of the individual scores, and therefore there is no impact on the standard deviation here. Okay, so now let's look at another transformation to see how it's going to affect things. In particular, let's start with this after our first transformation, and we can apply another transformation to the same set of scores. In particular, let's see what happens if we now multiply each score by a factor of 2. So we're going to take every single score and multiply it by 2. Those scores near 5 should end up near 10 because we're multiplying them by 2. Those scores that are near negative 5, you see here, should end up near negative 10 because we're multiplying them by 2. In particular, the way that's going to be represented is by this spreading out of all of the scores that we see. All of them have been multiplied by a factor of 2. Now it's hard to see here what impact this has had on the mean, because with the mean of 0, of course 0 multiplied by 2 is still just going to be 0. But as we know, a multiplication transformation does affect the mean by the same factor that it affects each of those individual scores. So in essence here, the mean has been multiplied by 2. The standard deviation is also going to be multiplied by 2, because we know that multiplication and division affect both the mean and the standard deviation. So we're going to multiply the standard deviation also by 2. And in particular then, this 4.70 becomes a new value of 9.40. And again, this makes sense with what we've seen here in the graphic. Because the scores ended up spreading out, okay, then we know that the standard deviation, the variability, should have increased. Okay? So remember, multiplication and division will affect not just the mean, but also the variability, whereas as we saw, addition and subtraction only affect the mean or the central tendency. In fact, it's going to affect all of the central tendency measures the same. It's also important to note here that the specific factor that you're applying applies to the standard deviation of the distribution that you see here. So it was specifically the standard deviation that has been multiplied by 2 in this situation. Now, we can do a transformation for a number of different reasons. We can transform a single distribution, and that's what we just took a look at, and we talked about some examples of that, like changing to deviation scores, changing the endpoints on a scale, changing from Celsius to Fahrenheit. But a lot of times what we want to do is to simultaneously apply 2 separate transformations to 2 different distributions in order to transform them to have a common mean and standard deviation. That is, to standardize them so that they are represented by the same underlying distribution. For example, what we may have are these 2 distributions you see here on the left. We want to compare scores across these 2 distributions. So what we may want to do is to standardize them by transforming both of them using different addition, subtraction, and multiplication or division operations independently to each of those 2 distributions on the left to transform them both to look like the distribution there on the right. Now let's look at an example of this finally to end this lecture. When we're standardizing scores, let's say that what you have is 2 different exams. Say you got a 78 on your chemistry exam and 89 on your stats exam, and so what you're wondering is, which exam did I do better on? Okay, so you're looking at this, you're telling your folks, let's say, yeah, I just got my exam scores back, a 78 on my chem exam, 89 on my stats exam. Okay, and depending on what your folks are like, they may say a number of different things. Great job on that 89 on your stats exam. But if you did so well on your stats exam, why did you do relatively poorly on your chem exam and get a 78? And you might try and convince them, well, listen, this exam was it was a much more difficult exam. The entire class did worse on this exam. But how can you formalize that concept? So the question we're asking here is based off of your specific exam scores here. You felt like you did just as good on your chem exam as you did on your stats exam. But how can we really look at that? Well, the way we can look at that is to look at the distribution of scores for each of those two exams and see whether, again, relatively, your score of 78 on that chem exam is indeed just as good as the 89 on the stats exam. And we're going to standardize these two sets of scores, these two exams, in order to do so. Well, in order to do that, what we need to know is we need to know about exactly that, the distribution of scores. Now, I'm going to use population notation here because we're going to assume that you're interested in this entire set of scores on the chem exam, that is your entire population. Okay? All of these transformation operators apply equally well to samples or populations, but again, just for precision here, we are indeed focused here about populations. On your chemistry exam, which we'll label as the variable x, and your statistics exam, which we'll label as the variable y. So let's say you have the following information, which, as I mentioned, you can typically retrieve from NICA in case unless your instructor has chosen to withhold that information. And you see that the mean of your chemistry exam was a 70 with a standard deviation of 6. The mean of your stats exam was 85 with a standard deviation of 3. And now what you then may want to do, again, is to transform these so they're represented by the same underlying distribution. And there's a number of different ways that you might do this. Okay, we're going to look at one example of this. Just looking at these values, let's say what we want to do is to transform the chemistry exam scores, that distribution on the left, to look like the distribution on the right. So that's the process we're going to go through now. So how might we go about doing that? Well, to standardize the scores, we want them to have the same mean and the same standard deviation. That's what we're looking for here. And so any operation we apply to this distribution of scores on the left is going to apply to each and every score, and depending on whether it's an addition or subtraction, or whether it's a multiplication or division, those operations are also going to apply to the mean and or the standard deviation. So just by looking at these, what we can see is, well, if we cut every score in half on this chemistry exam distribution on the left, we see the standard deviation on the left is 6, which is double the standard deviation on the right of 3. So we know that if we cut all of our scores in half, that is, divide everything by 2, it should also then divide our standard deviation by 2. That is, it's going to change that standard deviation of 6 to have a standard deviation of 3. So if we divide every single x score by 2, then what it's going to do is to make the standard deviations equal. So we're halfway there. That's the first step we want. But notice it's also going to change the mean of the distribution, because we know this division operation affects not just the standard deviation, but also the mean. So as you can see, it has changed from a mean of 70 to a mean of 35. Again, it has changed by the same factor as the operation we've applied. So again, like I said, we're halfway there. We've gotten the standard deviations to be the same. But now this mean of 35 on the left, it does not equal the mean on the right of 85. But hopefully you can see it's pretty simple to get those means to become equal. All we have to do is to then add 50 to every single score on the left. And what that's going to do is to add 50 to the mean then as well. It's going to slide that distribution to the right so that it has a mean of 85 now as well. And these two simple operations have now accomplished the feat that we wanted. What they've done is to convert the distribution on the left for the chemistry exam to have the same mean and standard deviation as the distribution on the right, i.e. the stats exam. Now remember, we're not applying these operations to just the mean and the standard deviation. We're applying these operations to each and every x score, which is shown by the equation there on the screen. And so what that's applied to is every single score, which has had an effect on the mean and standard deviation. But what that means is you can take any individual score and apply the exact same transformation to then compare it to scores on the right. And that's what you wanted to do in the first place. So what you'll notice is that if you take your individual score then of 78 on the chemistry exam and apply these operations in this order, first dividing by 2 would take your score of 78, divided by 2 and give you a score of 39. And then adding 50 to it would give you a score of 89. So in other words, when you transform your chemistry exam score so that it's on the same distribution that your stats exam is, it actually becomes the exact same score. In that sense, you've done equally well on these two exams, even though your raw scores may be somewhat different. So you can tell that to your parents the next time they chastise you for not studying as hard for your chemistry exam. So this is our example of a transformation, and specifically an application of transforming distributions in order to standardize scores. Now, this is going to lead into a topic that we're going to cover, and that you've probably covered in Stats 261, looking at z-scores, which are a very specific type of transformation and a specific standardization of a distribution to have specifically a mean of 0 and a standard deviation of 1. But that's getting a little bit ahead. We're going to save that for another day. End this lecture here with this example, and at this point you should be prepared to take the online quiz associated with this lecture material. Good luck.